Hey everybody, in this video we are looking at example 4 in the limits unit, lesson 1, focusing on piecewise functions. In this example we are being asked to sketch the graph and to identify the types of discontinuities, if any. Now, when you're starting out, I would definitely suggest doing it in exactly this order. First, you sketch, learn about the graphs, the picture, analyze it graphically. But eventually you should evolve to the point where you are able to identify the type of discontinuities, and or if there's a discontinuity without graphing, because you should be holding some pictures in your head. And I think that many of you out there should be at stage 2, right? You should be able to identify what's going on without putting the full picture to paper. So let's think about this for a moment, okay, before we actually graph. This first one over here, let's just erase these colors so we don't associate. Okay, here I'm going to have blue focus on this equation right there, right, this piece. So this piece is what? Well, it's a quadratic. Quadratic is under the umbrella. I know I talked about umbrella in the last video, but quadratics are under the umbrella of polynomials. And all polynomials have a domain of all real numbers, okay? So you have your umbrella. This is the polynomial umbrella, right? Underneath this umbrella, umbrella, okay? Underneath this umbrella are, for polynomials, you have, well, let's just shorthand. We have cubics, quadratics, we have linear, you have a constant, anything, right? Anything like this. These are polynomials, and what do they all have in common? Their domain is all real numbers. Their graph is smooth and continuous. There's no sharp edges. There's no pointy bits. There's no random end to the graph, okay? So all of these polynomials, when you see them in a piecewise function, you have to know that nothing is going to be causing you trouble, right? Other than its break, its restricted domain from the details on the side here, the graph is able to be drawn without an issue, okay? Now, what about the next graph here? The next graph here is the square root of x minus 2, and we have that graph to focus on when x is greater than 2. So what can we see here? For one thing, before I'm identifying any discontinuities, right, I know that my domain is all real numbers. Can you see how here we have everything to the left of 2, including 2, and then we have everything to the right of 2, right? So we have every x value is being used. Okay, great. Now, while this does not have a domain of all real numbers, what is the domain? Well, x minus 2, we should know, the radicand, must be then greater than or equal to 0. Therefore, x has to be greater than or equal to 2. So the domain is from 2 to infinity for the square root. So are there any issues when x is greater than 2? No. I mean, we just said 2 to infinity is the domain, and we're only worried about this from 2 on, like after the 2. So both of these have no abnormalities, nothing going on in the graph. So the only obstacle we might run into, the only discontinuity we might run into is a discontinuity brought on purely from the piecewise function. Okay, that's the only thing we might run into. So that being said, oh, go back. I just want to erase that. There we go. So that being said, how can I check if there is a discontinuity? Well, what could be at 2, right? What could happen? Is it possible, again, I'm trying to do this, I want you guys to do this visually. Is it possible, right, that you have your blue graph? Now, pretend you don't even know what it is. La, 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 la. You have your blue graph, and it ends. And we include where it ends at 2, right? So this is a colored in point where it ends. So we have our blue graph, and then our pink one takes over. Now, if our pink one takes over exactly where the blue one left off, well, there you go. Beautiful, continuous, happy times. So what has to happen for it to not be continuous. Okay, well, for it to not be continuous, oops, for it to not be continuous basically means that maybe, perhaps, the point at 2 is not defined. Maybe you have a hole, also known as a removable discontinuity, where one graph ends and the other graph starts. That's possible, but since we see our domains all real numbers, in this case it's kind of not possible, right? Well, what else is a possibility? Another possibility is that we have a jump discontinuity. We will not have an infinite discontinuity. That just isn't going to happen. So what would a jump look like? Again, we have our blue graph that ends somewhere, la la la, and then my pink graph will start at a different y value than my blue value leaves off at. So it's like you're in a relay race and you're passing the baton and you go to grab and the person's letting it go up too high and you drop it, right? So this is a jump discontinuity where one graph leaves off higher or lower than another graph is picking up. That's a jump discontinuity, and that definitely can happen. So again, how do we identify that? What did we say? At the same x value, they will have different y values. Their y values will not be equal to each other. Then you know it's a jump. We won't have an infinite discontinuity in this case because, well, we don't have any reason to understand there being an asymptote. So that's not what's going on. So let's analyze how we're going to do this algebraically. So algebraically, what we're going to do is, let's go ahead and do the mixture of the two colors, purple. We're going to check x equals 2 in both, in this case both, let's call it in both pieces. I was going to say equations, but in both pieces. So, and this doesn't look so good because this looks like a greater than sign. So I'm just drawing arrows. How about that? So it's not like a... Okay, so we're going to check x equals 2 in both pieces. And I want to see what output, f of x, what output do I get in both situations. If they match, I know it's continuous. If they don't match, then I know I have a jump. So over here, and I know like the bottom one's not even defined for 2, but we're just checking. That is it. So here I have 1 minus parenthesis 2 minus 1. Most of us should be doing this in our heads, I assume, right? And I'm just color coding. You have to come up with your own system to know what work goes with what thing. Because some of you guys, I don't know what to tell you. Your work is crazy. And then you can't go back and read it later, you know? 1 minus 1, 0. And then in pink, square root 2 minus 2, square root of 0 is 0. And what do I know? Well, 0 equals 0. So that means there's no, so the conclusion, right, for all this information, no, can I fit, I'm just going to abbreviate, no discontinuity, none. This is continuous. All right, so this is continuous. Now, could you do this with the support of a graph? Of course. This blue one, you might want to reconsider what it looks like. Maybe think of it more as negative in front, like that. X minus 1 squared plus 1. That might be more beneficial. Well, you can barely see that, right? Right, hello. Let's write it over here. Give myself a little space. Okay, so the blue one, you could think of it as y equals negative quantity of x minus 1 squared plus 1. I just turned it around so you could see a little bit better. So this negative is a vertical reflection. It's a parabola opening downward. I know it's a parabola because it's squared. X minus 1 moves it to the right 1 unit. Plus 1 at the end moved it up 1 unit. So the vertex is going to be right over here to the right 1, up 1. And it is opening downward, over 1, down 1. The pattern we all know and love for a parabola. And then I stop there on the right because that's already 2. And then over 1, down 3. Over 1, down 5. And so on. And there's the parabola. And then in pink, you have your square root graph. And really, if it helps you to think of it as y equals, like you have a 1 out front, square root of x minus 2. And really at the end it's plus 0, so up or down 0. 1 means, no stretch or compression, no reflection, nothing. Plain old, plain old. So to the right 2, open circle is where we start. It's square root graph, which is the top half of a sideways parabola, if you want to call it that. Up 1 over 1, up 1 over 3, and up 1 over 5. And there we go for our graph. Hopefully we could all see that pretty decent. And there you go. So where the one graph ends, the other graph picked up. So yes, could you graphically do it? Of course. Do you have to? No. So again, what do you do when you have a piecewise? Because guess what? If you take calculus, one thing you end up doing a lot is finding the limits at the x value where one graph ends and the other graph starts in a piecewise function. So you have to be able to tell, like, will I have a limit? And we just saw in the last definition, the limit is saying that we approach the same thing from both sides. Here you have a limit. Again, why? Because it's continuous. So I hope that this video kind of explained what we do and why we do it, and that you could apply this to more challenging examples. So if you followed and you are feeling happy and you love it, thumbs it up. No, mad, hate it, thumbs down. Questions, comments, concerns, feedback, requests, put it in the comments. Otherwise, hope you're happy, hope you liked it, and check the description or playlist for whatever else you need on this topic. That's it for now. Adios.